Yeah, I know. All right, here we go. It's going on page 77 when we're done. We are going to graph these two functions, log base 5 of x and y equals 5 to the x power down here. So I'm going to rewrite those as we do them so I don't have to scroll. So we're going to start with y equals log base 5 of x. Okay. All right, and we are going to go in here to plot some points. Okay, and I know that although logs are not brand new to you, that's still not something that you feel super confident with. Don't let us interrupt you back there. You good? You good? Okay. Okay, good. All right. So let's say that, you know, a lot of times when we go to just substitute in numbers, we start with like -1, 0, and 1. Those are good places to start. So if I substituted in a -1 and I got y equals log base 5 of -1, not something maybe you just know off the top of your head, but remember we can rewrite these as exponentials, right? I can write this as the base of 5 to the y power equals -1. So is there an exponent that I can put on that 5 that would give me a -1 as an answer? No, there's not, right? So let's say we change that -1. So -1, we get nothing, right? Let's change it to a 0. What if this was a 0? Is there an exponent that would give me an answer of 0? Think about that. Well, if I put 0 in for y, what's my answer? 1. It's not 0. So I get yes on that sometimes, but you're thinking the opposite way. There's not an exponent that I can take any number to where it's going to give me an answer of 0. You with me on that? So -1 doesn't work. Negative anything doesn't work. 0 doesn't work. If I put any positive number over here, could I come up with some exponent? Yes. I may need the calculator to help me, but like I could come up with it, right? Could it be a really teeny tiny positive number? Yes, as long as it's a positive number. So I can get really, really close to 0, but I can't use 0, and I can't use any negative numbers. But any positive number would work. You agree with that? Okay, so that means that my input for my log, I'm going to have a vertical asymptote. Oof, well, maybe. I'm going to have a vertical asymptote at 0, because I can't use 0 or anything negative, but anything after 0, even a teeny tiny positive number would work. Okay? So now, let's think about some numbers that we could use. What if I did log base 5 of 1? And if you don't know for sure, get out your notes from Monday, because up here, you have these basic properties. Oof. Well, I don't know what just happened there. You have these basic properties that you need to know. My board is being weird. Okay, here we go. And these are basic properties, things that you are expected to know. So log base 5 of 1 is going to give you what? 0. So we'll come back over here. Let's plot that point. So at 1, I'm going to get 0. Okay? What is log base 5 of 5? Look at your notes. It's 1. Get them out. Like, for real. You're going to need them. I'm going to ask you questions over and over again. Okay? So if I look back over here, log base 5 of 5 is going to give me 1. It doesn't matter. Log base 10 of 10, log base 1,000,000 of 1,000,000. You're going to get 1. So if I substitute in a 5 right here, that gives me a y value of 1. So 1, 2, 3, 4, 5, 1. Right there. Okay? The other thing that you have to know about logs, okay, that you really need to know about all of our basic functions, is what the parent function looks like. Okay? And again, they're not brand new. You graphed them in Algebra 2. You don't have to be a graphing wizard, but you do need to know that the parent function looks something like that. And since that said log base b of b equals 1, it doesn't matter what the base is. This point right here will be 1, 0 every single time, regardless of what the base is. This other point will change depending on the numbers, but the general shape is there. You with me on that? So those 2 points are really enough for me to sketch in my graph. It might take me a couple times up here. I don't always hit, oh, look at that, hit both points. Okay. There's my log. Yes, at the, what, x equals 0, but yes. Okay, we good with that? Okay, so now then let's look at our exponential. That was y equals 5 to the x power. So let's start, we started with -1 over there, let's start with -1 over here. What's 5 to the negative 1 power? 1 over 5, right? Gives me the reciprocal. That's why I can't get a negative number out of an exponent. All it does is give me the reciprocal. So that means I have the ordered pair, negative 1, 1/5, which is about right there. Now what if I substitute in 1? I'm sorry, let me back up. What if I substitute in 0? What's 5 to the 0 power? 1. So at 0, I'm at 1. If I substitute in 1, what's 5 to the first power? What is 5 to the first power? 5. So when x is 1, I'm at 1, 2, 3, 4, 5. And then again, what I need to know about exponentials, I have to know the parent function. You've been doing exponentials since Algebra 1. You know what exponential growth looks like. That's what your parent function looks like. So from the parent function only, just this graph right here, and not any other knowledge, anything, this right here tells you you're not going to get an answer of 0 out of an exponential, right? Are you going to get an answer that's a negative number? No. I mean, unless there's transformations, but just the parent function itself, there's no transformations. I can't get 0 and I can't get negative numbers because there's an asymptote here horizontally. So I only have 3 points there, but I do know what it's supposed to look like. I know it's not going to look like a parabola or anything, so I can sketch this in. Okay. And I sort of missed this point, but well, here, I'll try one more time, but it's probably going to be worse. That's why I don't always try a second time, but we'll see what happens. Okay, that's better. It's still not perfect, but it's okay. All right, so now let's write down what these ordered pairs were. This is 1, 5. This is 0, 1. This was negative 1, 1/5, right? And then this is 5, 1. And this is 1, 0. So looking at our two graphs, just visually and based on the ordered pairs, how are these two functions related? What are they? They are inverses of each other, right? So since they are inverses, that 1, 5 became 5, 1, 0, 1 became 1, 0. So is there another point I could put on my purple graph? Yes. I could go to 1/5, negative 1, and when I do that, the point's kind of right there, which I didn't hit it with my original graph, right? Totally fine, because it wasn't there, and we're sketching it anyway. I'm not going to worry about erasing it and making it better, but I can sort of connect it. So like the more points you have, the more accurate your graph gets, but we're not necessarily going for pure accuracy. Even if the points are in the right place, sometimes your curves get a little wonky, right? That's why having key points where they need to be and maybe labeling them, that works just fine. You're not going to have to graph on the AP exam. It is important that you graph by hand sometimes so you understand how it all works. That's why we don't have to be really worried about it being a perfect, beautiful graph, okay? Just sketching and getting the idea is good enough. So since these are inverses, these are reflections in which line? Y equals x. Very good. So let's sketch that line in. I'd put it in as a dotted line if I were you, but it's easier for me up here just to make it like a bright green line or something. So I'm going to cheat and do that. Okay, so the reason I'm re-recording, because I recorded this morning, but then last period when we got to this point, my board shut down, and I had to start over, and then my graphs were gone, and I didn't want to re-graph it to do the rest of it. And then I kind of liked the way I did it with last period anyway, so I decided to redo the whole thing here. Because what I did earlier today is I shrunk this down so we could look at this graph. Of course, you have yours in front of you, and then we could answer the questions up there. But I want to show you that, because this became a kind of a good teachable moment, that when we're up here and we're going to look at this information. Oh my God, I can't get my words out. So my log, instead of looking at my beautiful graph, which is fine, it's not that beautiful, but it's better than what I'm about to do, my parent function graph works just fine for me to answer these questions. Okay? And that's one thing I want you to understand. Just that simple little picture to have tied in your mind to logs, you can figure everything out you need. You don't have to graph absolutely everything all the time. So what is the domain? Where do we start? 0 and go to infinity. We never include the infinities. Do we include 0 here? No. Okay, good. What is my range? Very good. Negative infinity to infinity. All right. So then I have the limit as x approaches infinity of f of x. So as x approaches infinity, what is y approaching? Infinity. Y gets bigger and bigger and bigger, right? Now notice this doesn't say as x approaches negative infinity. This says as x approaches 0, then there's that plus sign. What does that plus sign mean? From the right. Good. As we approach 0 from the right, so as x is approaching 0 from the right, what is y approaching? Negative infinity. Very good. All right, so do I have asymptotes? Or an asymptote, yes. Horizontal or vertical? Vertical. So this is vertical, which means my equation is what? X equals 0. Yes. My intercepts, I can get that from this too. What is that point right there? 1, 0. Yes. And is this concave up or concave down? Down. Everybody okay with that? Okay, so now as we do the exponential part of this, I don't even need to look at a graph for domain and range, right? Because I know that it's the inverse of the log, so the domain and range just flip places, which means my domain is negative infinity to infinity, and my range is 0 to infinity. Now, there's nothing wrong with looking at the graph. I just want to remind you that those two things switch, because we are going to look at it. This is exponential. And so then you can double check, yeah, my domain is all real numbers, my range is 0 to infinity, right? Okay, do what? Would these two switch? Let's find out. As the limit x approaches infinity was x approaches infinity, what is y doing? What's it approaching? Infinity. As x gets bigger and bigger, so does y. Yeah. So no, they don't switch places. Because this isn't a switching of x and y where this is. Okay, that's a good question though. All right, so now this one does say negative infinity. So as x approaches negative infinity, what is y approaching? 0. Very good. Do we have an asymptote? Yes. Horizontal or vertical? Horizontal. Very good. So that means this equation is y equals 0. Very good. And what is this intercept? What is this? 0, 1. Okay. And it is concave what? Up. Okay. Everybody good so far? Okay. Any questions? All right. Flip it over. So now we're going to look at the natural log of x and y equals e to the x. So we're going to start off with y equals the natural log of x. Now, a log is a log, okay? We just looked at log base 5 of x, but we would have had all that same stuff up there if it was log base 10 or 20. Our graph at the bottom would have changed a little bit, but a lot of the important stuff stays the same. This is just a log. What's the base here? E. The base is e. So this is log base e. We just don't write log base e. It turns into natural log. It's really not any more scary or any different than the other. It just has a different way of being written. So my parent function looks exactly the same. So what is the natural log of 1? 0. This point right here is still 1, 0. I don't care what the base is. So the natural log of 1 is 0. So we can go to 1, 0 and make a point. Now, the one thing that helps you to graph these things is to have an idea of the estimation of e. If we're going to actually use e, we're going to put it in the calculator. Just like now, if you're going to actually use pi, you're not using 3.14. You use the pi button in the calculator, right? But it is important. It does help sometimes to know that pi is a little bit more than 3. I mean, there's things that you do where that's good to know, right? Even if you don't know, a little bit more than 3, a lot of times is good enough. So it is helpful to know that e is about 2.7. That's probably the only time you would ever actually write that down, just so that you know what it is, all right? If you have an answer and your answer is e, then you say or write e, but you think 2.7 when you go to graph. Does that make sense? It's like we would write 3/2, but we're going to think 1.5 when we go to graph, that same sort of thing. Because I don't want this to confuse you, and I don't want you to ever put 2.7 as an answer to something. You with me on that? Just like you're not going to put 3.14 if it's pi. Okay, you put the pi symbol. All right, so with all that said, what is the natural log of e? 1. You can look at your notes. Those are the basic properties you got to know. The natural log, and remember this. Although we don't write it like this, that would mean log base e of e? Well, log base 5 of 5 was 1, right? So log base e of e is 1. But again, we don't really write it like that, but you can think of it that way. So to plot the point, I'm going to go to e, which is about 2.7, and I go up to 1. There's my point. And because I know what my parent function looks like, and I also know that I have an asymptote here, I can draw that in, and then I can sketch in my graph. Ugh. You would think as the day went on I'd get better, but that doesn't happen. Okay, we good on that? All right, so then we're going to look at y equals e to the x. And I know this is exponential. There's no transformations. It basically looks like that. So what is this point right here? 0, 1. Because e to the 0 power is what? 1. Anything to the 0 power is 1. So e to the 0 is 1. What is e to the first power? E. E to the first power is e, right? That's what we say, that's what we write, but what do we think to the graph? 2.7. So I go to 1 and about 2.7. Okay? And I know that I have an asymptote here. Ooh. Here. So I then can sketch this in right here. And you can see once again that these are inverses of each other. And let's sketch in the y equals x line. I'm sorry, say that again? We don't need them. 2 points is fine. Because you know what the general shape is. We got more on the other one because we could and because I just wanted you to understand the graphs, but you don't need to. Okay. We good so far? So I did this one in addition to the other one because I don't want you to be afraid of the natural log and I don't want you to be afraid of e. I know you're way more comfortable with logs and you're not that comfortable with logs, okay? But people get scared of these and think they're crazy hard and it's really not that big of a deal. Sometimes the more weird things look and they are, the easier they are because they can only ask you so many things about them. Does that make sense? You can only do so much, so it makes it actually a little bit easier. All right, so let's go back up to the top here. And the natural log of x, that information is going to go here. My natural log looked like that, right? So what's my domain? 0 to infinity. Good. And what's my range? Good. Negative infinity to infinity. Then the limit as x approaches infinity is what? Infinity. And the limit as x approaches 0 from the right is negative infinity. Good. Do we have a vertical or horizontal asymptote? Vertical. So that means that it is x equals 0. What's the intercept? What's this point? 1, 0. And is it concave up or down? Down. Now, I'm going to leave this up here. You flip your paper over and look at what we wrote for. They're exactly the same. Because honestly, we didn't even go from our graph, right? We went from this, and that looks exactly the same for both of them. Yes? Okay, so not any more difficult just because it's natural log. So then you should be able to figure or write these out, right? Our domain, negative infinity to infinity. Range, 0 to infinity. Oh, and here's my little graph. Okay, not a bad idea to draw it and just think about it or be able to visualize it. As x approaches infinity, what does f of x approach? Infinity. As x approaches negative infinity, f of x approaches 0. What kind of asymptote do we have? Horizontal. So that means that is a y equals 0 line. What's my intercept? 0, 1. And up. Right. We good so far? Okay, beautiful. All right, any questions at all at this point? Okay, so grab your other set of notes. This is going to go on page 78. I do have these on separate pages because that just made sense to me. So. And we just looked at how they are inverses. So your general form of a log function, which is what we've been looking at, this has a little bit of a difference notes here, there's an a right there. We haven't had an a in front of there. What kind of transformation would that a be? Because it's the same as for any function we would do. It's a dilation. Is it vertical or horizontal? Vertical. If it's at the very front there, it's vertical because it's not affecting the x, right? It's after we take the log. It's also a stretch or compression because I've heard that a lot today. But remember, College Board seems to like the term dilation. I think it's still important to think of them as stretches and compressions, but make sure you know that they're all related. They're all the same thing there. Okay. So let's tie this to some exponential stuff. Because exponential functions and logarithmic functions are inverses of each other, we would expect the characteristics of the input-output values of an exponential to become the characteristics of the output-input values of a log. Because again, x and y switch places, right? So we are going to recall, because we did all this before Christmas, all the exponential stuff, for exponential functions over equal width input value intervals. So let's think about what that means, because we've heard that a lot, like since August, not just about exponentials. Because we've been looking at tables of data for a long time and focused a lot on looking at your x's and are these equal length input values, right? Because if so, then we can analyze some other stuff. If not, then we would have to do other things, right? Okay, so for exponential over equal length input values, the output values change multiplicatively. That's like a $10 word, I know. Multiplicatively. It just means you multiply by a number, that's all it means. Just sounds really fancy and hard. Okay, so when we look at this, it says notice how the input values are changing additively, or they're equally spaced. So here, we're adding 2 each time. It's okay, we don't have to be that fancy in our answers, but makes it sound way harder than it is. While the output values are changing multiplicatively, we're multiplying by 2. That's all that means. Multiplicatively. Multiplicatively. There you go. So here we're multiplying by 2 each time. So this is indicative, this indicates, this means it's an exponential function. I feel like on these sets of notes, because remember I get most of this stuff, I change things up a little bit sometimes, but from Mr. Passwater, and I felt like he was just having I don't know, he must have got like a vocabulary calendar for Christmas or something, and was just using big words. It's very odd for a math teacher to be just using the big words. But so what it's saying is, from what we figured out from exponentials was if your x values are changing additively or changing, equal length intervals, then your y values are being multiplied by something. That's what makes it exponential. Yes? Oh, it could be anything. Yeah, as long as you're adding the same number, whatever it is, and as long as you're multiplying, it doesn't matter what it is. Mm-hmm. Absolutely. Oh, yeah, they also don't have to match. Yes, absolutely. Yes, and we'll see those. Good question. Okay, so now let's look at logarithms. So for logarithmic functions, the 2 properties of input and output are reversed because they're inverses. Okay. So here we notice that the input values, are these equally spaced? No, right? But am I multiplying by the same number? Yes, these are, excuse me, changing multiplicatively. Again, we're multiplying by 2. That's all it means. While the output values are changing additively. Here, I'm adding 2. So since they are inverses, your x and y switched, so the properties switched as well, right? So when you don't have equal length input intervals, and your outputs are equally spaced, and then your inputs are being multiplied, that's what makes it a log. If you can figure out exponentials, logs just switch it around. That's all that's happening. Okay? So let's look how this happens, what happens here. It says selected values for several functions are shown below. For each, determine the given, if the given function can be logarithmic, exponential, or neither. So we look at this. Look at what's happening with your x values. Yes, they are changing additively. We are adding 1. And then are these changing multiplicatively? Yes, it's changing multiplicatively. What are we multiplying by? 1/2. Good. I know when you look at it, you think you're dividing, but we have to talk about it as multiplication. Yes?
So can we get away with it if we don't put the numbers side by side, like we just put it on the top?
Yeah, that's fine. I kind of did that because we don't really have room for all that, but yeah, that's fine. Just kind of saying the same, because you're going to write it out in your words here anyway. So do you think this is exponential, logarithmic, or neither? Exponential. Good. So we're going to say exponential. Okay. And then we can say our x values. Now I'm not going to use those big words, don't worry. X values are equally spaced. Well, you can if you want, but equally spaced. And then our y values are multiplied by 1/2. So it's kind of on the y's because you're being multiplied. It's kind of easier to say what the number is. And then for the x values, it's kind of easier to just say equally spaced instead of giving a value, and they mean the same thing. You just, okay? Everybody okay on that? All right. So let's look at B. Are your x values equally spaced? No. Are they being multiplied by the same number? Yes. So they're being multiplied by 3. Are your y values equally spaced? Yes. We are adding 10 each time. So exponential, logarithmic, or neither? Logarithmic. Okay, so okay, so on the AP exam, well, the math one anyway, your spelling doesn't matter. Okay, I always leave an A out of here. I spell this wrong almost every time. One reason I didn't is because it's in the question. But if you misspell something so bad you spell something else, that could be a problem. I've seen it happen before. But you don't have to stress out over the spelling. I could have said log here, and I think it would have been fine. But don't forget, you could also look at the question if you're trying to make sure you spell things right. But you don't have to focus on that too terribly much. So I would say logarithmic, and then I can say that my x values are multiplied by 3, and my y values are equally spaced. I'm sorry, what? Yes. There's just one official mock, but we'll do multiple things in class once we have more. Okay, so then let's look at C. Are your x values equally spaced? No. Are they being multiplied by the same number? Yes. Okay. So are your y values equally spaced? No. They're being multiplied by 2, right? So exponential, logarithmic, or neither? Neither. Okay, good. So neither. And I would say x values are multiplied by 10, and y values are multiplied by 2. If you don't, then you have to say something like they're changing multiplicatively or they're changing by the same number. You can't just say they're being multiplied. So to me, it's easier just to say what the number is. Okay, we good on that? All right, so you look at D, see what you can figure out, and then we will talk about it. You can go ahead and write out your reasons too. Do your words have to be exactly like mine? No. You just need to make sure that you're saying the right things. So that's what I got. Right. We don't talk about subtraction. We don't talk about division. It's all adding and multiplying, all of it. Okay. Anything else? So I got logarithmic, and I put x values are multiplied by 2, y values are equally spaced, right? Okay, something to that effect. Questions? Okay. All right, so exponential and logarithmic functions as inverses. That's what we were looking at with our graphs there. Now, it specifically talks about an exponential to log here, but this statement is true for all inverses, okay? If it's an inverse, then f of g of x and g of f of x, they both have to equal x. Okay, that's something we know in general about inverses, so of course it works for these as well. So we're going to recall, meaning we already know these things, graphs of inverse functions are reflections over the line y equals x, right? I think you've got that down. If the point x1, y1 is on the graph of f, then the point y1, x1 is on the graph of f inverse. Okay, that's just saying we're switching x and y, right? We all good on that? Okay. So then we are going to, it says let f of x equal 3 to the x, g of x equal log base 3 of x, and we are going to show that f and g are inverse functions, meaning they are inverse functions, show me why. You're not trying to figure out if they are, right? So we're going to start with f of g of x, which means I want f of log base 3 of x. So that would give me 3 to the log base 3 of x power. And log base 3 of x, 3 to the log base 3 of x power would give me what? Those of you that have your notes out like I asked, tell me. It's on the very top, where all those basic rules are. It's x. It's this right here. 3. This is 3 to the log base 3 of x power equals x. Remember, these are basic properties that you have to know. Okay? All right, and then we have g of f of x, which is 3 to the x power. So that would be equal to log base 3 of 3 to the x power. Can you find that on that chart? It would say log base b of b to the x gives you x. Okay. It's because there's a y there probably instead of an x, yeah. Yeah, so okay, let's look at that one then so you're not confused. Yeah, it's because there's a y there instead of an x. So it's whatever the exponent is, and that's why the letters are changed up, so you can see. Log base b of b to whatever exponent, your answer is just the exponent, whatever it is. Okay. Okie dokie. So we did that. We showed that they're both equal to x. We're good to go. Now, there's other ways to figure this out besides just knowing it, but it takes log properties that we haven't talked about yet that we will get to eventually. And if you know them, that's great. If not, I think it's just easier to know what you get from here. Okay. All right. So we have a portion of the graph of the exponential function. K of x equals 2 to the x is shown below, so they've graphed it for us. We're going to sketch a picture of K inverse, which is log base 2 of x on the same coordinate grid. So we can use our inverse concept, but we also know what a log graph looks like, right? And what is this ordered pair right here? 1, 0. There's no transformation, so it's just 1, 0. I could have totally gotten that from this graph, because this point is 0, 1, so that makes that 1, 0, right? Okay, and then I can, from the graph, I have an ordered pair of 1, 2, so this one becomes 2, 1. And then I have a point of 2, 4, so that gives me 4, 2. Okay, and we don't have to have all these points. I just want to make sure you know how to use all this stuff. Now, over here, I wouldn't get to guess at what these are, but I don't have to guess, because this one right here, I actually know exactly what it is, because the x value is -1. So 2 to the -1 power gives me what? 1/2. Which means this ordered pair is -1, 1/2, so I can go to 1/2, -1. And the more points you have, the better your graph's going to be. But again, you don't always have to find a bazillion points. Just want to make sure you know how we have an asymptote here, and then I can sketch in my graph. Whew. Something like that. We good with that? Okay. And again, you're going to have to graph on the AP exam? No, but understanding how the graphs work can be very important for you. That's why we do graph some of them. Okay, let's look here. So we have the exponential function, h of x equals a to the x. It contains these 2 points. We're going to find the average rate of change of this function. Well, how are these 2 functions related? They're inverses. So yes, this is y, but I could also call it h inverse of x. Would you agree with that? Okay, instead of y, I can say it's h inverse of x. And I want to find the average rate of change over this interval. Average rate of change means I'm looking for what? Slope. Pre-algebra, slope. Okay? So if those 2 points are in h of x, then the 2 ordered pairs I would get for h inverse would be what? 3, 2, and 27, 6. Okay? And what we are looking for here is the average rate of change over this interval. This is always an interval of the domain. So from 3 to 27, and I have the 2 endpoints of that domain that it's talking about. So when I go to find my average rate of change, it's the change in y over the change in x, right? So this is going to be h inverse of 27 minus h inverse of 3 over 27 minus 3. And every single time, I want you to write down the function version before you just start plugging in points, because that's going to help you get your y's separated from your x's and help everything hopefully get lined up correctly. Because it is the change. So these are the x values, 27 and 3. So h inverse of 27 is going to give me that y value. So then when I substitute those in, this gives me 6 minus 2 over 27 minus 3. That is 4 over 24, which reduces to what? 1 over 6. Now, one thing, I'm still not super sure that we'll even have a real answer before the AP exam, but I can tell you in calculus, you can totally stop right here, because nobody's testing your subtraction skills or your fraction skills. That's not what we're testing. We're testing, do you understand the average rate of change? And I've heard conflicting things about whether or not we really have to simplify all the way on the AP pre-cal test. Hopefully before the actual test I'll have a better answer on that, but until then we're going to keep on simplifying. And then maybe one day I can tell you can learn to just stop. Okay. Any questions? Which, believe it or not, stopping is harder than you think. Okay, that's sometimes things, that's something that people are challenged with, because they feel like you have to finish because you've always had to finish it off, right? Okay.